Today's lesson is going to be about subatomic matter. So we're going to look at things like what is matter and antimatter and how quarks combine. Now, a lot of this is just info, so I'm going to try and remember to tell you which bits to write down so that you know to write down and make your own notes from. So a lot of it is info heavy and the calculations are generally quite straightforward. So first of all, antimatter in fiction. Comes up quite a lot, certainly in recent movies. So in the movie Angels and Demons, an antimatter bomb is set off above the Vatican. But what is antimatter and can it do the things that we talk about in science fiction? So there's two links here. I'll save those for you to watch. And you can see the first one is from the movie Angels and Demons, and the second one is a more fact-based one about what antimatter is and what it can do. Okay, so this slide's really important and I would like you to copy the information on this slide here. And this is our definition of what antimatter is. It is simply that antimatter consists of material with the same mass as the corresponding matter, but opposite charge. So for example here, we have our matter particles here, electron, proton, neutrons and neutrinos. And we have their symbols here, E for electron, and remember there's a negative because an electron has a negative charge. P for a proton and a plus there because there's a positive charge. Neutrons and neutrinos both are neutral, so that's why we have a zero there. We'll be using this notation again when we do radiation. So the antiparticle version of the electron, you can just call it the anti-electron, but because it's such a special case, we call it the positron. And notice how it has an E plus there. Protons, antiprotons, with a P minus there. Antineutrons and antineutrinos, notice it still stays as zero because it was zero to begin with. Now, one thing to note here is that the antiproton, you might think, well, it's got a negative charge, so why is it not just an electron? Well, if we go back to a definition, remember, antimatter has the same mass but opposite charge. So we can't say an electron and a proton are the antimatter versions of each other, because remember, a proton is much, much more heavier than an electron. So the antiproton is a proton that has a negative charge. Now, antimatter can be written as the following. So if this is the matter version, then the antimatter version is just the same symbol, but with a line above it to represent it's the antimatter version. So this would be the antiproton. If we're talking about the neutron, N would stand for neutron, so N with a line above it would stand for the antineutron. Now, how do we make antimatter? Well, it's a really, really energy intensive process, and it is made in CERN, but they can only make tiny, tiny amounts of it, around about maybe 1 or 2 grams of antihydrogen. And there's lots of reasons why they can't make a lot of it. Number one is because it's very energy intensive. Number two, you can't really touch it. So the only way you can contain it and deal with it is by magnetic fields and electric fields. And one of the reasons why you have to use these electric fields is because if matter comes into contact with antimatter, they will interact and destroy each other. And we'll talk about that a bit later on. So just to zoom in now onto our quarks and antiquarks. So these are our quarks. Now these are called subatomic particles because they are smaller than your atomic particles such as protons, electrons and neutrons. So this is us really delving deeper into what matter is made up of. So we've got 6 types of quarks: up, down, top, bottom, strange and charm. And the antimatter versions of these are simply anti-up, anti-down, anti-top, anti-bottom, anti-strange, anti-charm. So you need to know the names of these particles. And remember, the antimatter version still has the same mass, but the opposite charge. And we'll talk about that a bit later on as well. Similarly, we have leptons called anti-lepton particles. And again, we'll talk more about these later on. We've got leptons are electrons, muons, and tau. And there is also a neutrino version. So you have an electron neutrino, a muon neutrino, and a tau neutrino. And each of these have their own antimatter version. So this would be the positron, because remember, the antiparticle of an electron is the positron. The anti-electron neutrino, the anti-muon, the anti-muon neutrino, the anti-tau, and the anti-tau neutrino. And as I said earlier, matter and antimatter will annihilate each other, releasing a lot of energy. So that's worth writing down as part of your notes. And annihilate is a technical term that we use, so be able to recognize that and use it in the proper way. Now, appreciate there's lots of terms here, lots of particles. I don't really expect you to remember these off by heart, but I do expect you to recognize these when I show you them. And we're going to build on our knowledge of what these particles are in the next couple of slides. Because matter and antimatter annihilate each other, they release a lot of energy in this process. And again, in science fiction, there is this idea that we could power spaceships using an antimatter drive, and that's mentioned in Star Trek there for our sci-fi fans. Okay, so now let's try and look deeper into what our quarks and leptons are. And this slide here, I would say, is probably the most important one in this lesson. So I would make sure you copy it and you try and learn how to draw this diagram and explain the different parts. Because if you can do this, if you can draw this diagram and explain what each of these bits are, then you'll have understood most of the stuff you need to know for particle physics. So this is a diagram that shows the standard model. And remember, the standard model says that all matter is made up of particles. And there are two branches of particles, matter particles, which are called fermions, named after Enrico Fermi. You might remember him from our semiconductor lessons. And bosons, which are called force-mediating particles. And the most famous one you've probably heard of is the Higgs boson. And we'll look at these at another lesson later on. Today, we're going to focus on the fermions, and in particular, the hadrons and leptons. So the hadrons consist of particles that are made up of quarks. So these can be divided into two more groups, the mesons and the baryons. And I've given you an example of each, so it's useful to give an example of each. So mesons are, for example, are kaons, baryons are protons. Leptons do not consist of quarks, and these are electrons and neutrinos. So I appreciate a lot of new terms, a lot of particles. It does take time to get your head around it, but doing this diagram and being able to go down this tree, I find really helps. So let's get some more definitions. Hadrons are particles made from quarks, and two quarks joined together will give you a meson. So an example of these are the zero kaon, plus kaon, and mesons. Three quarks joined together are called baryons. So examples of these are protons and neutrons, and these are made in the Large Hadron Collider in CERN. Okay, now mesons are usually made of a quark anti-quark pair. So again, I don't expect you to memorize any of these names and what quarks combine to give you, say, a pi-0 meson. I just want you to be comfortable looking at these and saying, well, there's two quarks there, so it must be a meson. Now, you might say, well, if matter and antimatter annihilate each other when they interact, then how can these particles exist? And the answer for this is simply that these particles have a very, very short half-life. So because this is made of a matter antimatter, they do interact and annihilate each other, and they therefore exist for a short lifetime. But there are wee tricks that allow these to be detected, and we'll look at this a bit later on. So baryons are made up of three quarks called triplets. So examples of these are protons and neutrons. So protons is made up of an up and a down quark. So up, up, down. Neutrons is made up of an up quark, a down quark, and a down quark, or up, down, down. And these can be represented by diagrams like this. And these basically show you the bonding between the quarks here. So these are called triplets. Now remember, we also have antimatter versions of these, so antiprotons and antineutrons are also baryons because they are also made up of three antiquarks. And you can see it's anti-up, anti-up, anti-down, anti-up, anti-down, anti-down. And I've switched my notation now to be underneath it, but that's still okay. So how do particles combine? How do all these particles combine? Well, first of all, quarks and leptons are fundamental particles, and that means they can't be broken down further into smaller particles. They are the basic building blocks of matter. Now, there are theories which suggest that quarks themselves may be made up of things called strings, but that's going into a whole different theory which is beyond the standard model. What we're interested in is how do quarks interact to produce different particles. So let's think about protons and electrons because we're familiar with those. What's the charge of an electron and a proton? Hopefully you can tell me it's a negative and a positive charge. Okay, and in atoms, electrons and protons will generally tend to pair up. And what I mean by that is, if you think about an atom, you've got a positive nucleus where all the protons are gathered together, and then orbiting around that nucleus are your electrons. And the reason why the electrons orbit around the nucleus is because there's this attraction between opposite charges. And so that's how we describe an atom. So quarks also have a similar interaction, but let's look at them in a bit more detail. So here are our quarks. So we've got our up, charm, top, down, strange, and bottom. And there's 3 generations of these because the first generations were the lightest ones, and they were discovered first because they needed the least energy to break them from each other. And then the heavier ones, you can see these are using giga electron volts. So these were discovered later on because they need more energy to break them up. So quarks have a charge of either plus 2/3 or minus 1/3. So you can see here in our diagram. Now, if you ask me why is it 2/3 and not a plus or a +1 or a -1, the answer is I can't tell you. This is just how nature has created quarks. And this is where Feynman very famously said, if you ask a why question, you can always keep asking why. But if you ask a how question, you can kind of explain it because it suggests as a mechanism. So how do these charges interact? Well, first of all, because they're fractions, do you think quarks will form pairs? Well, hopefully the answer is kind of no, because we've talked about baryons and mesons, haven't we? So we know that baryons have 3 quarks called triplets, and mesons have pairs of quarks and antiquarks. So the answer is generally no, they tend to form triplets, and there's a reason for this. So here's the reason. The rule for combining quarks is that the total charge must always be a whole number. What do I mean by that? Well, if we take the charge for an up quark and a down quark, remember it's plus 2/3 and minus 1/3, then for a proton, there are 2 ups and 1 down. So that's the same as saying, let's add 2/3 to 2/3 and add, a minus 1/3. Now, if you do this in your calculator, we get the charge is +1. And that's actually really good because what is the charge of a proton? It's +1, isn't it? So this is really nice because it means our quarks not only are consistent with the physics, because when you add them together, you still get the charge of the proton. It really just kind of ties together. Now let's try it for the neutron. We've got an up, down, and a down. So you try it yourself and then I'll show you the answer. Hopefully you know that, well, there's 1 up, so it's 2/3, plus minus 1/3, plus minus 1/3. So if I write that down, then if you add this together, you will see that you get 2/3 minus 2/3, which is equal to 0. And again, that's nice because it fits with our physics, our current understanding, which is that the neutrons have a 0 charge. And that's always really important. So try some of these yourselves. If you go back a few slides, write down what the charge for an up and a down charge, a down quark is, and work out the charge. Remember, for an anti-quark, it is the opposite charge. So if the up quark was 2/3, then the anti-up would be minus 2/3. If the down was minus 1/3, then the anti-down will be plus 1/3. And remember, mesons are still made of quarks, so the charge must still be a whole number. And hopefully what you find is that the charge corresponds to the symbol here. So this should be positive, negative, neutral, neutral, so on and so forth. Now, let's get to some past paper questions just to show you how this works. So pause the video and have a wee read of this yourself, and then I'll take you through the answers. Okay, first question, it says, explain what is meant by the term fundamental particle. So the first thing is, a particle cannot be broken down into smaller particles. So it's just a straight recall question. State the name given to the group of matter particles that contains quarks and leptons. And again, it's a straight recall question, hadrons. Next one, determine the total charge on the pentaquark. So that's the symbol for the pentaquark. And they very nicely give you the charge of what the quarks are. Now, at the start of the question, it gave you that a pentaquark is made up of 2 up, 1 down, 1 charm, and 1 anti-charm quark. So pause the video and see if you can work out what the charge on the pentaquark is. And then I'll go over the answer with you. Okay, hopefully you got the following. It is 2 times 2/3 because there's 2 up quarks, plus minus 1/3, plus 2/3, and plus a negative 2/3. Because remember, the charm has the opposite charge to its matter. The anti-charm has the opposite charge to its matter version. And then if you add these two together, you should get a charge of +1. And next one, so again, have a read this yourself and then pause the video and I'll go over the answer with you. Hopefully you got that because it's a quark anti-quark particle pair, then it must be a meson. Okay, final question here now. So read it and have a go of it yourself. I'll take you through the answer once you've tried it yourself. So hopefully you weren't put off by the fact that this is a calculation and that it is in fact a special relativity one. And this is also one of the reasons why we can detect quark and anti-quark. It's because in a particle accelerator, these particles are traveling close to the speed of light. So that means they experience relativistic effects. So their half-lives, the time they exist, is actually a lot longer. Now, if you're not sure how to do this, I will do a power-up lesson on it at some point, but it's our usual KFC technique. V is 0.91 C, time is 8 times 10 to the minus 21 seconds, and we're looking for the dilated time. Otherwise, we wouldn't be able to detect these quark antiquarks. And it's just a case of plugging this into your equation and solving it. So I will leave you to do that yourselves.